Okay, so as we continue with this partial fraction decomposition, okay, the whole point of doing this is to take a fraction, like we're kind of working backwards than what we did last year in Algebra 2, right? You have two fractions, you make common denominators, you add them together. That's what you did at the end of Algebra 2. Now we're taking the all together and we're breaking it apart, okay? Why is that helpful? Well, when you get to calculus, you do this thing called integration that you don't know about. And it can be helpful if we can break these apart into multiple fractions to where it's easier to do this integration, okay? It can be used for other things, but that would be probably the most immediate thing that you would see. So, yesterday, okay, and then on the board for our problem of the day, these were the steps, right? We have to factor the denominator and write the problem. Okay, if it's a linear factor, we want a constant in the numerator. If there's a repeated factor, we have to include all of those powers. And if there's a quadratic factor, then the numerator must be linear. Okay, adding on to those steps. Okay, I think it was Miss Cronky's voice last night, right? But did she have these steps for you? Okay, so adding on to those steps, what we're going to do is we're going to multiply by the LCD on both sides. Okay, basically whatever your denominator is originally, that's what we're going to multiply on both sides so that we no longer have fractions. And then we're going to solve for our A, B, C, D, E, F, G, whatever constants we have. Well, A, B, C, and D are the constants that we're solving for. We're not going to consider them to be variables. Okay. Now, I am going to show you two different ways to do that. The first method I'm going to show you is what I call substituting in zeros. That's probably the easiest way to do it. However, it's not going to work 100% of the time. It's not going to help us in cases like this second one we did, where we have a quadratic factor, because there is not a real zero we can plug in there, okay? So I'll show you a second way of comparing coefficients, okay? Now, it seems kind of random that we were like solving all of these linear equations and now we're like doing this, right? Well, when we do this method right here, we could have to solve a system, and that's why it's in this chapter, okay? So we're going to go through, I can't remember how many examples, I think 4 examples, and my goal will be to get through these 4 examples so that you can do a couple in class before you leave, okay? And then tomorrow, we're going to have a short little quiz based on this partial fraction decomposition to see if you really understand it or not, okay? So, I didn't do this yet, I apologize. Okay, so this is what we set up today in our problem of the day. Do you agree? Okay, so we already decided that the denominator was x plus, say 4 times x plus 2. And we wrote out a over x plus 4 plus b over x plus 2. Now, some of you may have set that up as a over x plus 2 and b over x plus 4. If that were to happen in a problem, like a homework problem, where you and your neighbor just have the order switched, all that means is your A and B are going to be switched. You're still going to get the same answer. Okay? So you know what? This is what I'm going to do. Just for a better visual. Okay, what I'm going to have you do with each problem, I'm going to have you multiply by the LCD. The LCD is always going to be the denominator of your original problem. So we're going to multiply by x plus 4 times x plus 2. Why? It gets rid of all of our fractions. Okay? So if we multiply this by that green LCD, we're left with x plus 8. If we multiply this fraction by the LCD, then the x plus 4s cancel out, and we're left with the a times x plus 2. Plus, if we multiply this fraction times the LCD, the x plus 2s are going to cancel out, and we're going to have b times x plus 4. Oh, that's nice, right? No more fractions to deal with. Okay. So my method of substituting zeros is this. Okay. Look right here. What would make this factor 0? -2. So let's plug in x equals -2. If we do that, we have -2 plus 8 equals a times -2 plus 2 plus b times -2 plus 4. Okay. All we did is we plugged a number in for x. We can do that. Now, what happens? This goes to 0, right? So 0 times a. We don't have to worry about it. We get 6 equals 0 plus 2b, which means b equals 3. Then we can do that again. Okay, but this time, what should we plug in? Okay, we want to make this go to 0. So we can plug in x equals -4. When we do that, we get -4 plus 8 equals a times -4 plus 2 plus b times 0, right? So what's a? So then the very last step, which I must not have shown you, would be to actually write the decomposition that got hidden by my screen shade and I forgot it was there, okay? After we solve for the constants, we actually have to go back and write out our decomposition. So if once we get all of our constants, okay, this is what we can do. Our original problem was x plus 8 over x squared plus 6x plus 8. That is the same thing as a over x plus 4 plus b over x plus 2. If you found common denominators to add these two fractions together, we'd get back to this right here. And that's what we're doing. Questions on that? Okay. Go ahead and write this one down. It is not necessary to factor the denominator, the numerator, but it is necessary to factor the denominator. Eli, how do we factor the denominator? Take out an x. To what? You're not wrong.
1 plus 1. Or x plus 1 times x plus 1.
Okay. So this can become x times x plus 1 the quantity squared. What case is this? We have a repeated factor. So let me ask you this question. How many factors do we have in the denominator? We have 3, which means we're going to have a sum of 3 fractions. Should have wrote those a little smaller. There. Our first factor is x. Since it's linear, we'll put a constant upstairs. Upstairs. Okay, so how about our second 2? What would the denominators be for the second 2? Nick? Okay, x plus 1 and x plus 1 the quantity squared. If you have a repeated factor, you have to include all of the powers. So if it was x plus 1 cubed, you would have x plus 1, x plus 1 squared, and x plus 1 cubed. Okay, you have to represent all the powers. This is a linear factor, so a constant upstairs. What do we consider this to be? Linear or quadratic? Since it's a repeated linear factor, we still treat it as a linear factor. Okay. All right, so we are going to multiply by x times x plus 1 the quantity squared because that is our LCD. Okay. So when we multiply this fraction, denominator cancels out and we're left with the numerator. Okay. When we multiply this fraction, we know that the x's cancel and we're left with x plus 1 the quantity squared times a. When this second fraction multiplies over, only one of the x plus 1's will cancel. So b is going to be left to multiply to x and x plus 1, because only one of them cancel. But then when this third fraction multiplies over, both x plus 1's cancel and we're left with c times x. All right, so what do you want to plug in? Okay. Okay, so if x equals 0, okay, why are you picking 0, Nick? Okay, since we have a factor that is x, 0 will make that 0. Okay, so if we plug in 0, we have 5 times 0 squared plus 20 times 0 plus 6 equals a times 0 plus 1 squared plus b times 0 plus 1, and then plus c times 0. What are we left with? We're left with 6 equals a times 1. So a is 6. Woohoo! We're on our way. All right. Lindsay, what else could we plug in?
-1.
Okay, let's plug in -1. We have that x plus 1 factor, so -1 is going to help us. All right, so if x is -1, okay, we're plugging in -1. Okay, so when we have 5 times -1 squared plus 20 times -1 plus 6, what is that going to leave us with? What's 5 minus 20?
-15.
Plus 6? -9. Okay? And over here we have 0, 0, minus c. So c is going to be 9. Okay? Have we found all 3 of our constants? No. And we have run out of factors to make 0. What are we going to do? Do we know A? Do we know C? Can we plug anything into X? We can plug anything into X. Okay? So if we know C and we know A, and we can plug numbers in for X, that only leaves us with B, correct? So if you have this case of repeated linear factors, and you're looking for the last constant, you can plug in a random value. Now, be careful with this random value. Don't make it too complicated. What would be a very easy number to plug in? 1. We could plug in x equals 1. We know that A is 6. We know that we don't know B. And we know that C is 9. So we can plug in x is 1, we can plug in our A and C, and so now all we have left to figure out is B. Okay? This is only going to happen if you have a repeated linear factor. Alright, so what do we got here? What is 5 plus 20 plus 6? What is it, 31? And then we have 6 times 4 plus 2b plus 9. Huh. What do we end up with? What do we end up with? equation. 5x squared plus 20x plus 6 all over blah, 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 blah equals A. What was A? 6. A over x plus B over x plus 1 plus C over x plus 1, the quantity squared. Okay? Now, if you would like, instead of saying plus a negative 1 over x plus 1, you could just do the subtraction of 1 over x plus 1. I don't care how you write it, but know that that's probably what the back of the book is going to write. Okay? There you go. There it is. Okay, that's 2 out of the 4. Our third example you have already set up. Okay, so if you need to rewrite it down in the place where you are in your notes, that's fine. But this was our second example for the problem of the day. So we factored the denominator to x times x squared plus 4. X squared plus 4 cannot be factored any further. That's fine. So we have 2 factors in our denominator, which means we're going to add 2 fractions together. X and x squared plus 4 were our factors. Since x is linear, we're going to put a constant in the numerator. Since x squared plus 4 is quadratic, we place a linear expression in the numerator. Okay. Just like before, we will multiply by the LCD. Okay. That will always be the denominator, so that will always cancel everything for the fraction on the left. So 3x squared plus 4x plus 4. When we multiply a over x, we're left with a times x squared plus 4. When we multiply x squared, or this third fraction, the x squared plus 4's cancel, and we're left with bx plus c, the quantity times x. Please be careful. Make sure that that linear expression in its entirety is being multiplied to whatever factor's left over. Okay, so now you can see our problem. Yeah, we can plug in 0 to get rid of this, and we can easily find a. But there is no real number we can plug in here to help us find b and c. So we're going to have to move to an alternate method. Okay, so for these last 2 examples, I want to show you what I call comparing the coefficients. Okay. So what I'd like you to do is I'd like you to multiply everything out on the right side. Ax squared plus a times 4 plus, so I distributed the a through. If I distribute the x through, we have bx squared plus cx. And just so that it's easier for us to see, I am going to arrange these in order. So I'm going to put my x squareds together, then write my x term, then write my constant term that doesn't have an x. Okay. So comparing coefficients. Here are are my two x squared terms. What's the coefficient of x squared over here? 3. So what should be true about a plus b? If we have these two expressions that are equal, then when we combine like terms, the coefficients must be the same. So our x squared coefficients better add up to be 3. What about our x term? Our x term over here is c times x. Our x term over here is 4 times x. What does that tell us? C equals 4. Okay. Our constant. Our constant on the right side is 4a. Our constant on the left side is 4. Those better be the same. What? It's kind of nice, isn't it? This system of equations is pretty nice. They won't all be this nice, which is why you can do this method every single time. I just can't promise you it'll be the nicest systems of equations every time. But you can use it every time. I do not care. Okay? All right, so what does this mean? This means a equals 1, right? And if a equals 1, what is that going to mean about b? 3. B has to equal 2 since a plus b equals 3. Okay? So we can go back and say, all right, well, originally we had blah, 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 blah. I just like to rewrite it. You don't have to do this, but what we had originally we can write as a over x plus bx plus c over x squared plus 4. It was nice, wasn't it? I like these. I think they're enjoyable. Okay. It's a nice way to apply systems of equations. Okay. Now that was a nice system of equation. You know, that didn't take a lot of work for us. They may not always be that nice, but sometimes they could. Okay. All right, one more example, and then I'll have you do a couple from your homework, okay? Okay, can we factor x squared plus 2? Okay. We can't. So it's x squared minus a number we can factor, x squared plus a number, not going to be helpful. So what we have is a repeated quadratic factor. What happens when we have repeated factors? How many factors do we have? We have 2, so how many fractions do we need? Okay, we have to represent it both times. As many times as it is repeated, we have to represent it that many times. So, we have to represent this with 2 fractions. One having a denominator of x squared plus 2. What is the second denominator? X squared plus 2, the quantity squared. Okay? Since they are quadratic factors, your numerators need to be linear. So I would say ax plus b and cx plus b. Okay? You'll notice that I just start with a and I go in order. You can do whatever you want to do, but I think they're nice letters to work with. Okay? You guys commenting on all the letters and numbers? thank you. Pay attention. Okay, so what do we multiply by? Whatever your denominator is, that's what you're multiplying by. Okay. So that's always going to cancel out. 8. And it's always going to cancel out the denominator on the left. Please be careful with how you write this. X squared plus 2 cancels out with one of these. So you have the quantity ax plus b times the quantity x squared plus 2. Your third fraction. The denominator cancels out with all of what we're multiplying by, so we're just left with cx plus d. Anytime you have quadratics as your denominator, even if there's 1, you have to use the comparing coefficients method. Okay? So, if we're going to do the comparing coefficients method, what do we need to do over on the right side? Multiply all those out, okay? So, ax times x squared, ax times 2, b times x squared, and b times 2. Just gotta multiply those out. Now, since these are in order, I just really like to put these in order, okay, on the right side. So I'm going to rearrange to ax cubed plus bx squared plus 2ax plus cx plus 2b plus d. Okay, 6 terms, and I rearranged 6 terms. Okay, so this one actually works out pretty nice as well. Okay, we have a cubic function that equals a cubic function. Their coefficients better be the same, right? If we have 2 equal equations. So I have 8x cubed. Here I have 8x cubed. What does that tell us? A equals 8. We've got one of them. Okay? Here I have bx squared, but I don't see an x squared over here. So b is 0. Exactly. The coefficient of x squared is 0. Okay? Now here, I have 2 terms that are adding together to be x. Over here, our x coefficient is 13. So we need to write that 2a plus c equals 13. And then same thing over here. Do you see a constant? No. So what needs to be true about 2b plus d? If there's no constant, what should they equal? 0. Okay, so we have A and we have B. Let's go to here first. If B is 0, what does that mean about D? D is going to equal 0. Okay? Over here, we have 2a plus c equals 13. We know A is 8. What is that going to mean about C? -3. Okay. So now we have all 4 of our what? So, AX plus B. AX plus B. I'm not going to write the plus 0. You can, but it's not necessary. And then plus CX plus D. Or that second denominator. All right. So you have 7 minutes, and I want you to get done one problem. Now, instead of everybody like trying to find their book, what's the first bolded problem on your homework? Number 20?
Yeah.
Yes? So I'll write number 20 on the board for you. That way you don't have to do the whole carousel of trying to find your books and yada, yada, yada. So I want you to get number 20 finished before the bell rings. And if you get done with number 20 and there's time left over, then go to the next one. So number 20 is this, and then your next bolded problem is 23. So I'll write it down in case you have time to do 2 problems. You are not just setting them up. I want you to solve them out. Okay? Solve them out. But I don't want it to be quiet in here because I want you to be consulting with your peers and checking each other's work and answers.